Hello everybody. I'm going to be talking today about the history of the development of physics, from the broad sweep from Aristotle all the way up to quantum mechanics and the current day. And I'm going to be relating that, or trying to relate that back a little bit to the spiral in terms of looking at it in the context of the societies and the sort of historic periods in which it's set and how those might kind of interact with each other. I should say that I volunteered to give this talk because I've given a similar talk to a Buddhist group, so I'm kind of recycling some of my research here. So, and I'm not an expert on the history of science or physics, nor an expert on spiral dynamics. I've only sort of encountered it about a year ago, but I'm interested in both topics, and so this was a good opportunity for me to sort of try and link the two and dig a little bit deeper. I should also say that I do have I have a PhD in particle physics, so I've got plenty of experience of the culture of physics and kind of the stories that physics tells, about itself. So at least I can bring that to the table. So let's get started.
You have more knowledge than us, that's for sure.
Okay, great. So just to set the big picture and the kind of sweep that we're going to go through here, I've got about 16 slides, so let me start a timer so I don't lose track of time. The history really spans a very long period, depending where you want to mark the start point. Certainly more than 2,000 years, maybe more than 2,500 years. And in this sort of telling of the story, we're going to start off in ancient Greece. You can obviously go further back than that to ancient Egypt, Mesopotamia, and to other cultures as well, India, China, and parallel developments in other great civilizations such as the Mayans, etc. And I've used the kind of what's now almost a retro sort of thing, but his story. One thing that's very notable about the history is it's very, very male dominated. And that's still the case in the field. It's still about 80% male, though that is beginning to change slowly. Obviously, there are very famous women in the history of physics, but a lot of them are, maybe less prominent or just outnumbered by the sheer sort of quantity of men, and probably many have been written out or just forgotten altogether. We're going to be looking at the collision of worlds, particles, and ideas. So a lot of the time there was physics is set in a sort of context of conflict against the societal values and norms of the time. We're going to be looking at ideas of complexity and mastery, the role technology, power, and persuasion play. Also want to kind of examine a little bit the idea of the sort of truthful out. So what you see, physics has its own kind of trajectory as part of the whole sort of scientific endeavor, and that's a sort of an allegiance to a sort of transcendental idea of truth and the reality of nature, which is has its own thread regardless of the society where it's taking place. And then towards the end we'll look at physics in the second tier and the culture of academic physics. So just a sort of complete overview of this telling of the story, which is a very compact telling of the story given the long sweep of it. And as I said, we're starting in ancient Greece with the pre-Socratic philosophers. We'll go through the early Christian period, which is sometimes referred to as the Dark Ages. We'll touch on the Islamic Golden Age, then onto the scientific Renaissance, Galileo and Copernicus. We'll look at Newton and the classical physics, so-called classical physics, which covers mechanics, gravity, and optics. We'll then go on to look at the Industrial Age, where a lot of that worldview of Newton was sort of expanded and consolidated and refined. And then we'll get into the sort of the breakdown of that worldview with Einstein and the quantum revolution, as I'm calling it here, which introduces themes of uncertainty, probability, and issues of general relativity. And also in the technological sphere, we end up with the atomic bomb in that phase. And then the sort of the subsequent post-war, post-Second World War phase, which I'm labeling here as the sort of period of grand unified theories, which more or less leads up right up to the present day. So that's the big sort of sweep of history there in terms of physics. So I just want to keep my notes in queue here. So I think one thing, starting this version of the story in ancient Greece, we could have started in Egypt or other places, but it's quite common to start it in ancient Greece. And I think that's partly because European culture and Western culture has told itself so often over its own history that it's descended from the kind of the Greek culture, that's effectively almost become like a self-fulfilling prophecy. So lots of origin stories in all sorts of areas of Western culture would usually sort of take ancient Greece as its starting point. And certainly it was a kind of a fascinating society, and it's kind of hard in some ways to place it, in any particular single bracketed value mean, V mean on the spiral, because there's so much different type of activity going on. So you have a pantheon of human-like gods. Maybe that's a sort of a purplish, bluish type structure. But you also have a competing marketplace of ideas with established philosophical schools, all trying to outcompete each other for sort of influence and relevance. You have experimental politics going on, and experimental public policy going on in Athens, where they're continually changing their constitution to try and get a balance between all the different factions and interests. You have empire building and so forth. And in amongst this, we have Aristotle, who was a student of Plato and also tutor of Alexander the Great. The reason we're picking him to say let's take him as the starting point here is really because of his subsequent influence in later periods. He comes to be seen as possibly the most important of the Greek philosophers in later periods. Though at the time there are many other very interesting views, which would include all sorts of things such as like a heliocentric worldview, so a view of the solar system with the planets going around the sun, which is in contrast to the Aristotelian view. There were atomic theories. There were all sorts of ideas which kind of predate most of what we might think of as ideas from the Enlightenment or whatever. And the Enlightenment either revisited or rediscovered some of those ideas. So, and another reason for picking Aristotle is he published a book called The Physics. So it's a kind of first coining of the term physics in this kind of sense. But really it's touching on kind of natural philosophy, so the philosophy of natural phenomena. And he's interested in moving bodies and the natural place of things. So it's not an empirical kind of study, it's more an observational study, and it's looking for sort of themes of harmony and the natural order. And things, rare events were kind of seen as aberrations that didn't really require any attention. So it was more kind of interested in the kind of steady state or the natural state of things, so-called. Okay, oops, I'm going too fast there. So following the remarkable sort of flourishing of ideas and culture within the Greek period, that gets transferred over to the Romans, who were, when they thought of scholarship and philosophy, they look back to the Greeks. Most of the philosophy was still sort of in Greek. If you were interested in philosophy in the Roman times, you'd have to learn Greek typically. Some of it was translated, but certainly not everything. And then the Roman Empire adopts Christianity, and then around about the sort of 4th, 5th century, there's a significant decline and fall of the Western Roman Empire. So I'm characterizing this period as sort of the early Christian period. And in this time, you see a loss of interest in philosophy unless it's applied to specifically to theology. And truth is no longer something that can be found through reason. It's more something that's found through revelation and the Bible. And the notion of heresy emerges, that you can go against the sort of diktats of the church. So this is a sort of strong blue memes, type of V memes arising here. And this period would later be referred to as the Dark Ages by Italian scholar Plutarch, who is considered to have promoted the notion of this period as being a kind of period of cultural decline and darkness compared with the light of the classical age. And natural philosophy in itself certainly isn't of any particular interest. Okay. So, and that kind of then brings us to the Islamic Golden Age. So in parallel with this, the Eastern Roman Empire, or the Byzantium, as it's referred to, or the Byzantine Empire, didn't really fall. It sort of continued, and then Islam arose and expanded, and it more or less absorbed the remnants of Greek and Roman culture within it. And then Islam itself had a sort of rapid expansion in terms of territory and economic success, and that gave it a kind of confidence that led to kind of an emergence of strong orange kind of style V memes, particularly around the start of the Abbasid dynasty in 750 AD. And a particular library, sometimes referred to as the Grand Library of Baghdad, or the House of Wisdom, was established around that time. And there was a sort of a command sent out to all the scholars to gather texts from all around the world, from the Greek, from Greek traditions, but also beyond that, from China, from India, and so forth, and Persia, and to have them all translated into to Arabic. So there was this really outward-looking, open interest in scholarship and wisdom, and it wasn't only a sort of a museum-type activity. These sort of the texts were actually then studied and then practiced and turned into living traditions again. So you can see it as a sort of a real revival of the Greek traditions, Greek mathematics, and so forth. And the scholars who worked in the House of Wisdom were also acting as physicians or consultants or architects and so forth. So it's a very active revival of the Greek tradition here, and that included the natural scientific elements, in terms of the astronomy and aspects of mechanics and so forth. Okay, there's one sort of caliph of note here. Caliph Al-Ma'mun he sort of provided direct financial support for the House of Wisdom and was even involved in its day-to-day affairs. And it was said that his love of science was so great that he preferred scientific texts as the spoils of war. So maybe he was a kind of philosopher king in that sense, that he was very, very interested in knowledge and wisdom. Okay. And without the Islamic Golden Age, we probably wouldn't have had, or at least not in the same shape, what comes to be called the Renaissance and then the scientific Renaissance. So around about 1050 onwards, the Western world starts getting very interested in sort of the ancient Greek texts, and there's a sort of a thirst to reacquire that knowledge or that interest. So after the fall of the Western Roman Empire, the knowledge of Greek had basically died out in the West. There was very few people who could even read it anymore. So it wasn't, it effectively had been lost. Many of the texts had been lost. There was very, very little knowledge of that sort of classical Greek culture. And Western Europe looked to the Arabic world, the Islamic world, as a source of those texts. So there was a sort of a move to kind of acquire those texts and translate them back into Latin, and that accelerated, and that became the Renaissance, which is a period that can be considered to span about 300 years, from about the 14th to 17th century. And towards the end of that, we see what we now think of as the scientific renaissance, or the scientific revolution. And interestingly, then at this time, as the texts were reintroduced, Aristotle's worldview with the Earth, his view of physics and the view with the Earth at the center of the sort of planetary system, became the church orthodoxy. But the overall sort of flourishing of Greek thinking led to a sort of cultural flourishing that was typically sort of humanistic in its character, meaning that it valued human experience and intellect and insights, and wasn't always deferring to sort of heavenly higher authorities, and that kind of put human reason back into the foreground. And as a result of that, two major figures sort of come forward: Copernicus and Galileo. So Copernicus was a Polish canon of the Catholic Church, but also a mathematician and astronomer and all-round polymath. And from his astronomical observations, he effectively rediscovered the heliocentric model of the planet. So that's where the planets, including the Earth, go around the sun. And this was in direct conflict with the sort of current church Aristotelian orthodoxy at the time. And this was a time when, to contradict the church, you basically faced charges of heresy, which could lead to corporal punishment and so forth. And so he didn't publish on this until just before his death in 1543. And at the time, his works attracted very little direct criticism. But over time, as their influence grew, the church became more and more concerned, and eventually stated that the heliocentric theory was heretical, basically. So the Copernican view was an heretical view. And then in sort of half a century later, Galileo comes along. He was an Italian astronomer, physicist, and engineer from Pisa, and he studied the properties of matter, motion and acceleration, and objects under gravity. And he also made very detailed astronomical observations using the new technology of telescopes. He became the first person to ever observe Saturn's rings. And he published some essays in support of the heliocentric model of Copernicus in 1610. And as a result, he faced the Inquisition, the Roman Inquisition, in 1615. And the Inquisition declared the heliocentrism to be foolish and absurd in philosophy and formally heretical, since it explicitly contradicts in many places the sense of Holy Scripture. So here we see a kind of clash of this emerging scientific sort of memes with the value memes of the societal order as embodied by the church and its orthodox teachings. And Galileo was ordered not to sort of touch the subject, and he stayed clear of it for about a decade. But he was friends with Cardinal Barberini, who later became Pope Urban VIII in 1623. And I think the fact that he was therefore friends with the Pope gave him courage to pick up his project again, and he published a work on the heliocentric system in 1632, but with the formal authorization or formal permission of the Inquisition and the papal and the Pope, basically. And this book was in the format of a dialogue between different characters discussing the different views. And unfortunately, Galileo had been asked by the Pope not to give arguments both for and against the heliocentric view, and to be careful not to be seen to be advocating it, so not to be in clear, direct opposition to the church view. But unfortunately, Galileo called the character who was advocating the Aristotelian sort of earth-centric view, geocentric view, named him Simplicio, which was actually named after a sort of famous Aristotelian philosopher. But in Italian at the time, the word or the name Simplicio had the connotation of a simpleton. So it was almost saying it was like a simpleton's view of the world. And at the time, this made the Pope feel publicly humiliated by Galileo. And it was also suggested that the Pope himself was fearful of not being seen to defend the church sort of strongly enough. And so Galileo faced the Inquisition again. And this time he was found vehemently suspect of heresy. So he wasn't actually formally charged with heresy, but kind of as good as. So that meant he didn't have to suffer corporal punishment, but he was basically put under house arrest and told not to, not effectively sort of stop publishing. And his books, his works were forbidden, including any he might write in the future. But while under house arrest, he worked on another book, sort of steering a bit clear of the astronomical issues. And these were about his sort of theories of materials and motion. And that book was published in 1638. And that's sort of provided a very important foundational text in the study of moving, of sort of bodies in movement and so forth. So here we can see the interaction between cultural memes and the tension between religious blue and humanist orange attitudes. And we also see in Galileo's defiance the beginning of an emergence of an allegiance to a notion of mathematical and empirical truths that transcend societal authority, and that kind of idea begins to play a bigger and bigger part in the story physics tells about itself. Okay, so that then brings us to Isaac Newton, who's a key figure in the scientific revolution. And in his work, the Principia, he basically synthesizes and sort of completes or extends all the known kind of key results of physics at that time. So that would include the sort of the studies of motion from Galileo, but he also formulated a theory of universal gravitation and did work on optics. So in sort of story of physics, Newton is usually seen as the father of modern physics, and the kind of sets the real foundation stone for everything that kind of comes subsequently. But in addition to this, he had very unorthodox views on Christianity, which he mostly kept to himself. He was a fellow of Trinity College at Cambridge and a professor of mathematics there, but he refused to be ordained into the Church of England, which was normal at the time, and actually sought personal dispensation from Charles II. And he was also a secret alchemist. So 10% of his writing is on, of his notes, personal notebooks, were on alchemical themes. So he was kind of savvy enough of a political operator not to publish those or make them public knowledge, along with his most of his unorthodox views on Christianity. But they were certainly kind of key and important to him. Yeah, he was considered a very politically savvy and astute operator, and tended to win all of his battles, basically. So he became president of the Royal Society. He ran the Royal Mint. There's an interesting story about him actually going into bars in disguise to find counterfeiters, people who are forging coins and stuff like that. So he's a very interesting kind of character. And in his memoirs, even though he was kind of very revered and kind of fierce in terms of his kind of competition in his career, he said, and whether this is bluff or true, but he famously said, I do not know what I may appear to the world, but to myself I seem to have been only like a boy, playing on the seashore and diverting myself now and then, finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. So I think he felt there was you know, the bigger truth or the bigger picture was all out there undiscovered. In terms of physics, this kind of Newton effectively creates what's now referred to as kind of classical physics, or the classical physics worldview. And this is a kind of, in terms of within the culture of physics, this is a kind of sort of blue type meme in terms of it's a sort of immutable order. It's a worldview that's kind of set, authoritative, immutable, and kind of isn't really to be challenged. And you know, given that Newton was so such an avid devout Christian, he may have seen this view of the world, which is quite a mechanical view, as you know, as God's grand design, or you know, a type of it's a given sort of structure. So I'm now going to sort of switch to the next 200-year or 300-year period quite quickly. I'm going to refer to the next 200 years as the Industrial Age, and quite a lot's happening in this period. So we have the expansion of the British Empire, we have the Industrial Revolution, and this has a sort of strong interaction with the evolution of physics. So physics in its own terms is trying to sort of complete or extend the Newtonian project, and really it's applying those sort of approaches and methods to all of physical phenomena. So there's a kind of land grab within physics to try and, you know, tackle the next discovery and to analyze it in the using the methods of classical physics. And quite a lot is achieved in this time. So specifically, well, there's an interplay as well between physics and what's going on in the economy. So often the demands from the economy or from the Industrial Revolution are driving certain lines of inquiry within physics, and specifically thermodynamics is a field that was worked on basically to try and work out how you could achieve more efficient steam engines. So that was a direct kind of interaction there. And then from the other way around, when Faraday and Maxwell did their work on electricity and magnetism, that was very quickly commercialized and led to, you know, a lot of the inventions that would kind of dominate a lot of the 20th century, such as radio, telegraph, telephones, domestic mains electricity, eventually television and so forth. So that all has that technology all has its origins in this period. This, we can clearly see here sort of strong orange memes of entrepreneurialism, you know, a lot of individual endeavors to excel in the field and to really make a name for themselves and so forth. But in terms of physics, the way it sees itself as well, I'd say at this time it was kind of there's still a kind of a blue meme within the culture of physics, in that it has this stable worldview. It's quite excited by what it's achieved, and it also has a sense of mastery. It's a sense of that it's kind of effectively mastered the physical world and can sort of bend, you know, or can apply this knowledge of the physical world to create new sort of amazing technologies for humankind. And the role of technology is quite interesting as well, in terms of how technology effectively acts as the salesman for the scientific worldview. So the fact that people benefit from the technological products of science encourages this sort of view of science as being this very valuable and kind of, you know, true kind of worldview. But unfortunately, that not quite complacency, but that kind of settled attitude of feeling quite established and really having a grip on what was going on comes to an end very quickly at the end of the 19th century and the early 20th century, as more and more startling discoveries were made. So as the scientific sort of investigation continued, particularly at the small scale, the scale of the atom, strange results sort of started to emerge, and this kind of forced weird sort of statements that would have seemed mad or even crazy to the classical physics worldview, the previous generation had felt so proud of, and even to normal common sense. So statements like atoms are almost entirely empty space, light is made of particles, energy is discrete or lumpy at the tiny scale. There is an opposite type of matter called antimatter. Matter behaves like a probability wave until an observation is made. And then it has to jump randomly to just one of the available measurement values. Or a particle of matter is in a sense everywhere until I make a measurement. Particles can go through barriers. There is an incredible uncertainty there is an irreducible uncertainty in some pairs of measurements, like position and momentum. And the vacuum is not empty, but fizzing with temporary particles. And if this wasn't bad enough, Einstein developed his general theory of relativity, which was published in 1916. And this corrects Newton's theory of gravity by saying that, that space and time are linked, that you have to see space and time as of a piece, they're one structure together, and that the apparent force of gravity is simply due to curvature in this space-time. So space-time is warped by the presence of matter. And so things move along what appear to be sort of deviating lines due to this warping of space-time. And this period was like a midlife crisis for physics. It took a long time for the physics establishment to accept quantum mechanics, because it's kind of so crazy and you can't really understand what's going on, underneath the mathematics. But the mathematics works incredibly well. This was all happening against a global backdrop of imperial and continental wars, increasing use of technology in all areas of life, including warfare, and the rise of Marxism and major political upheavals. So while physics was having its kind of nervous breakdown, kind of the old social orders were kind of having a similar kind of breakdown at the same time. This leads us to the atomic bomb, and I'm putting this in because this, within the history of physics, this wouldn't normally be given so much importance, but in terms of the relationship between physics and sort of human culture, I think it's very striking importance. And many physicists, many famous physicists of the 20th century, were involved in the creation of the bomb in the Manhattan Project. Yeah, so you can see this as an extremal point in the application of the new physics to the technology of warfare, and it rewrote the relationship between physics and humanity. Maybe that, you can see this as the beginning of the turn of the tide, where people maybe start doubting that scientific progress is inherently an inherent good for humankind, or is necessarily positive or beneficial. And maybe this can be summarized in the famous quote from physicist Oppenheimer, who ran the Manhattan Project. Translating from the Hindu text, the Bhagavad Gita, he said, "I am become death, the destroyer of worlds." So there's a sense that maybe humans have become almost too clever for their own, or at least technologically too clever for their own good. So whilst many physicists involved in the project may have been deeply shaken in a moral sense, physics itself marched on in its pursuit of ever deeper, more accurate understanding of the world of quantum particles. And sort of, one of the most key, or one of the key experiments in this is CERN, that straddles the French-Swiss border. You can see the circle there. There's effectively a particle accelerator that runs in a circle underneath that, where that line is marked. It's vast. And what they do there is they accelerate tiny sort of subatomic particles to incredible speeds, near the speed of light. So they have huge amounts of energy, and then they just smash them together. And when you smash them together, the energy in the particles actually makes it possible for effectively new particles to be created, and then those particles decay, as it would be the word they use, but effectively transmute into a sort of smaller, lower mass, lower energy particles, which are then picked up in the detectors. And what CERN has been investigating for the last, basically the whole post-war period, well, since it was established, is what's called the standard model. And the standard model is a combination of the particles we know or believe to be fundamental, and the theory we believe describes how they interact, which we call quantum field theory. And this is an incredibly accurate theory that can produce predictions that are accurate to like 8 or 9 decimal places. So it's phenomenally accurate. But the problem with it is that it leaves certain things unaccounted for. And it has certain mathematical features which kind of, to a theoretical physicist would say, this isn't a complete theory. This is, even though it's incredibly good, this isn't a final theory. This isn't complete. So what that has led to for most of the last, say, 30 to 40 years is the search for grand unified theories. So there are four kind of known forces in the universe, and these, physicists feel that these probably should be just one force, and maybe these are just different facets or faces of one particular force. You also get 3 identical copies of the same particles, but just heavier. And that's a sort of a strange mystery in itself. Why should there be 2 copies of the electron, one called the muon, one called the tauon, that only vary in the fact that they're heavier than the electron? So you get these 2 carbon copies of the basic lighter particles. Also,
sorry,
yes.
Which 4 forces are you referring to?
I'm referring to electromagnetism, the weak force, the so-called strong force, and gravity.
Thank you.
And so really there's a drive within physics to try and find one theory that unites all of these. Also, quantum field theory can't account, at least in its current form, can't account for gravity. The Einstein's general relativity would still be seen as a classical theory in that it's not a quantum theory, whereas physicists feel that the world is fundamentally quantum mechanical, and therefore there should be a quantum theory of gravity. So that's, yeah, and this project is still ongoing. As yet, there is still no one theory that can achieve this, but there are theories like string theory, which have been fantastically successful in some ways, but they have almost another problem, that they almost explain too much and predict things that we don't see at all, like higher spatial dimensions and even more forces and stuff like that. So yeah, but it's a wide open field, and this is still the main concern of most, certainly particle physicists and particle theorists. I'll just touch very briefly on the culture of academic physics. So having been in academic physics, I would describe it as being something like a cross between a priesthood and Star Trek. Priesthood in that there's a sense of being devoted to the search for truth and the high, the true order of nature and the true model and so forth, but also going to sort of the final frontiers and the new boundaries. So it's a strange sort of priestly-like activity. There are huge egos and rivalries, but also massive collaborations. CERN has hundreds and hundreds of physicists all working on it, and when they publish a result paper, all of the names of the people currently working on the project are listed on every single paper that's published in alphabetical order. So so they make it very clear that that's just one huge collaborative experiment and project there. There's this belief, certainly in the theory community, of truth and beauty. So you often hear phrases like from various physicists, like, I knew the equation had to be true because it was so beautiful. So there's this sort of strange kind of Platonic kind of themes of kind of higher truths that maybe exist in some kind of realm of Platonic ideals. But okay, so that's just a little side comment there on the culture of academic physics. And then finally, we'll touch again on quantum mechanics. So as an undergraduate, when you talk quantum mechanics, everybody's mind is completely blown by all of the weird statements, this talk of the wave function, the so-called wave function collapse, when it suddenly has to randomly jump into one of the available values, and the fact that the sort of standard interpretation of quantum mechanics, the so-called Copenhagen interpretation, which is that the particle is evolving as a kind of probability wave until you make a measurement, and the measurement has to be made by a conscious observer. And when a conscious observer makes the measurement, then you get that wave collapses into a single value according to the probability distribution. So there's plenty of weirdness in there for philosophers to spend millennia poring over. And pretty much all of the major figures who've ever kind of worked on quantum mechanics or played a sort of foundational role in it said, if you think you understand quantum mechanics, then you're wrong. So Feynman, who basically developed the kind of quantum field theory, he just said he didn't understand it, and if you think you understand it, then you probably don't. But from a physics point of view, that doesn't really matter, because physics is primarily concerned with measurement, and the mathematics tells you very, very precisely how the measurements will behave. So physics can actually proceed, which is why the project was able to proceed with work on the standard model and search for the grand unified theories. But more recently, as people have become interested in issues of consciousness, trying to understand human consciousness and so forth, that this issue of the conscious observer has kind of come to the fore again, and people are trying to sort of interpret what this wave function might mean, or what even quantum mechanics means. And I find it quite fascinating in sense of, that if you go back to the Newton quote, that quantum mechanics might simply be telling us that the true nature of reality is in some sense fundamentally unknowable, which echoes turquoise and some teal memes there. And I think a lot of people feel or have some kind of intuition that there may well be some kind of convergence with physics and consciousness, because this issue is so much at the core of quantum mechanics, and consciousness in itself is so deeply mysterious that they feel that maybe there's going to be some future convergence between these two fields, though no one can really tell you what consciousness is. Okay, so that was our whirlwind tour through the history of physics, from Aristotle to quantum mechanics, and I've got a couple of questions for the groups, if these make sense. So the first is, what is the relationship between scientific theories and technology, and the society in which they are embedded and evolving? And the second is, compare the evolutionary forces in the history of physics and the history of societies. So whether they're similar or different. That's two suggested questions there. So I'll stop the presentation there. Thank you.